Hello, my name is Runa Chatterjee, and today I'm going to run two inferential statistics tests. The first one is going to be based on the data that you have in front of you. The first column is student absences per semester, and the second column is semester average. And my goal is to see if I can find any correlation between these two variables. Let's look at the research document. The research question here is, how does absenteeism relate to semester averages for students at a local high school? Null hypothesis states there is no relationship between absenteeism and semester averages for students at a local high school. Research hypothesis, there is an indirect relationship between absenteeism and semester averages for students at a local high school. The statistical test that I am going to run is called the Pearsons Coefficient test. This is a parametric test where independent variable is absenteeism and dependent variable is the semester average. Lowercase r is the symbol for Pearsons coefficient. There are two possibilities. Either r is equal to 0 or it's not. If r is equal to 0, that indicates that there is no correlation and that our null hypothesis has not been rejected. When r is not equal to 0, we conclude that there is some kind of correlation between the two variables, in which case the null hypothesis is rejected. This r can be a negative or a positive value. So the first thing that I'm going to do here is to run Pearson's correlation. And that gives us a negative value of 0.971. Two things about this value. Number one, it's a negative value, which means there is an indirect relationship between the two variables. Second, this number is very close to 1, which means the correlation is very strong. Going on to the r square value, this will be simply the square of this number. And that is a very high value as well. 94.34% means that variance in one set of variables can be explained up to 94.34% by the other set of variables. In other words, we're looking at maybe 5.66% of the variance which is not being explained by these variables. So as far as p-value is concerned, that is the most significant part of this test, because this value is going to tell us if we are able to reject or not reject our null hypothesis. The alpha value, the threshold of significance, is set at 0.05. Now for finding p-value, we're going to run a regression test. So going to data analysis, okay, I have to get out of this box. Let us select the Y input and then let's select the X input. We do not have any labels. The output range needs to be that. Okay, so we have a bunch of different pieces of information. Out of these, I'm really interested in looking at the p-value right here. This p-value is extremely small. It is not a 0, but almost a 0. Now, since this p-value is so much smaller than 0.05, we are able to say that the null hypothesis has been rejected. So, two types of findings from our Pearson's correlation test. Number one, there is a correlation between the x and y variables, which is very high, and they have an indirect relationship amongst them. And second finding is that the p-value is smaller than the alpha. Therefore, we stand to reject the null hypothesis. Trying to remind you of what the null hypothesis was, we rejected this. We rejected that there is no relationship between absenteeism and semester averages, which means we accepted the research hypothesis. Now, a couple of assumptions that we had made in this test is that our data points were under a normal distribution curve, and we can quickly plot that bell curve in order to clear that assumption. So mean would be the average of all these values. Standard deviation would be that of the sample. And then distribution is found by normal distribution of the first value, the mean, standard deviation, and then false. And very quickly, I'm going to freeze these values over here. And if I drag all of this down up to the last data point, it's going to overshadow a little bit of this, but that's all right. These are our distributions, and degree of freedom is actually the total number of observations minus 2. So count all of these, which is 18, and 18 minus 2 will give us the degree of freedom. So going back to trying to plot a bell curve, we will select all these values and go to insert a bell curve. As we can see that it is a very nice bell shape. It's a little squiggly, but it still maintains a good normal curve. So our assumption is right, that our values fall under a bell curve. And the other assumption was that our data is linear, and we can work on that by selecting all of our data and insert a scatter plot. So these points look pretty tight to each other. They are almost along a straight line. We can even introduce a trend line, and as you can see, the points are either on the line or hovering very close to the line. Therefore, our assumption that they have a linear relationship is also fulfilled. The sample was collected by simple random sampling, and it is continuous data by ratio measurement because we have number of absences and we have a semester average. So that concludes my first part of inferential statistics analysis. Moving on to part 2, and here is my data. I'm looking at academic achievement awards given in STEM and non-STEM areas, and if there is any relationship between those awards and the gender of the students. So these are the observed values of the awards given according to male and female students. Quickly, we will draw our attention towards the research question. The research question here is, what is the relationship between gender and number of STEM and non-STEM academic excellence awards given to the students at a local high school? Null hypothesis is that there is no relationship between gender and number of STEM and non-STEM academic excellence awards given to the students at a local high school. Research hypothesis says there is a relationship between gender and number of STEM and non-STEM academic excellence awards given to the students at a local high school. The name of our test is chi-square test of independence. It is a non-parametric test. Independent variable are the number of STEM and non-STEM awards, and dependent variable is gender, male and female. So we will find expected value. So if we are assuming that there is no relationship between gender and the STEM and non-STEM awards given, then there should be an equal distribution. So the expected values can be calculated by multiplying the total number of male students times total number of STEM awards divided by the total number of awards. Male times non-STEM awards divided by total number. Female students 60 times STEM divided by total number, and then female students times 54 divided by total number of students. Now if you would see, these are exactly the same totals as the observed values. And if we want to give a cursory looks to the numbers, we will see that they aren't too different. 25, 21, 19, 23, 25, 29, 35, 31. Now let us do actual tests to see if there is indeed any relationship. Let's work at the chi-square values of these individual fields. So this can be done by subtracting the observed value minus expected value squared divided by the expected value. Observed value minus expected value to the square divided by the expected value. Observed minus expected squared and lastly observed minus expected divided by the expected. Okay. No, this does not look right. Observed minus expected There you go. And now we will add up all of these individual values. So this is going to become 1.21. This is going to become 1.12. Yeah. And then we will add these two up, which becomes the value of chi-square, which is 2.33. Now, what is the significance of chi-square value to be 2.33? We have set our threshold of significance, which is alpha value, to be 0.05. Let's quickly reference the chi distribution chart. Okay, we did not talk about degree of freedom. That is required for us to reference that chart. Degree of freedom can be found for a 2x2 chi-square test. 2 rows minus 1, 2 columns minus 1. 1 times 1 is 1. So degree of freedom in our chart here is 1. Now, for degree of freedom to be 1 and our significance to be 0.05, the threshold value of chi-square is 3.841. Now, our value of test statistic is 2.33, which is less than 3.841, which is our critical value. This means we were trying to find out chi-square value because we were trying to find if there's any relationship between the two. Now, since we did not meet with the critical value, we can say at this point of time that we do not see a relationship between the gender and the awards given in non-STEM and non-STEM areas. Further, we can prove some more of it by finding the p-value, which can be done by running a test called, running a formula called chi-squaredist, where we will select the numbers both from observed and expected, no, something went wrong here. So this is going to be chi-square test. The actual range and the expected range. Our p-value is 0.51, which is higher than the alpha value 0.05, and in this case we can say that we have not been able to reject the null hypothesis. Once again, since p-value is higher than the alpha value, we have failed to reject the null hypothesis. So quick reminder that our null hypothesis was that there is no relationship between gender and number of academic excellence awards, and we have not been able to reject this. Therefore, this stays true. Further, in order to calculate the effect size for 2 by 2 chi-square test, we can use the formula for running finding the value of phi, which is the effect size for 2 by 2 chi-square test. We can put in a formula that is equal to the chi-square value divided by the total number, and everything raised to the power square rooted. So phi value is 0.15, which is a very small value. It's not a 0, but it's a very small value, and that indicates that the number of awards are not substantially different from each other. And that was one thing that we had talked about when we started, that these numbers are not very different from each other. Therefore, to cap our findings once again, our chi-square value was 2.33, which was lower than the threshold, which means that there is not a relationship between gender and the STEM and non-STEM awards. Our p-value was 0.51, which was higher than the alpha value, which indicates that we have not been able to reject the null hypothesis. And finally, the effect size was 0.15. That indicates that similarity or the differences between the two sets of values observed and expected were not substantially different from each other. And quick look at the test assumptions. We assumed that we have categorical independent variable, which is true because our independent variables were STEM and non-STEM awards. We have categorical dependent variable, which is true also because those were male and female. And third assumption was that the variables consist of 2 or more categorical independent groups, and which is true as well because both of them have 2 and 2 groups each. That is the end of my inferential statistics analysis.